and uncovering the secrets of the cosmos. The intricacies of how galaxies generate and maintain their magnetic fields. Detecting magnetic fields in distant galaxies presents a unique challenge for astronomers. These fields are not only invisible but also incredibly faint, making their detection a complex task that requires innovative methods and advanced technology. Unlike stars and galaxies that emit light, magnetic fields are invisible to the naked eye. They don't shine or glow, and their presence can only be inferred through indirect means. So, how do we see these elusive forces? The answer lies in the ingenious techniques developed by astronomers over the years. Astronomers rely on clever techniques and sophisticated instruments to detect and study galactic magnetic fields. These instruments are designed to pick up the faint signals that magnetic fields leave behind. One such method involves observing radio waves emitted by galaxies. These radio waves can carry the signature of magnetic fields, allowing astronomers to study them from millions of light-years away. When charged particles encounter a magnetic field, they spiral around the field lines, emitting radio waves in the process. This phenomenon, known as synchrotron radiation, is a key indicator of magnetic fields in space. By studying the polarization and intensity of these radio waves, astronomers can map the strength and orientation of the magnetic field. Polarization provides clues about the direction of the magnetic field lines, while intensity reveals their strength. Another powerful tool is the observation of polarized light. Polarized light waves have their electric fields vibrating in specific directions, which can be altered by magnetic fields. Light waves can be polarized, meaning their electric fields vibrate in a specific direction. This property of light is crucial for detecting magnetic fields in space. When light passes through a magnetized medium, its polarization is altered. This change can be measured and analyzed to infer the properties of the magnetic field it encountered. By analyzing the polarization of light from distant galaxies, astronomers can infer the presence and properties of magnetic fields. This method allows them to study magnetic fields that are otherwise undetectable. Instruments like radio telescopes, equipped with sensitive detectors, are crucial for these observations. These telescopes can detect the faint radio signals that carry information about magnetic fields. The Very Large Array, VLA, and the Atacama Large Millimeter, Submillimeter Array, ALMA, are prime examples of such telescopes, enabling astronomers to probe the magnetic fields of galaxies in unprecedented detail. These arrays consist of multiple antennas working together to provide high-resolution images and data, making them indispensable tools in the quest to understand the magnetic universe. Not all galaxies are created equal when it comes to their magnetic fields. Each galaxy, with its unique structure and composition, harbors a magnetic field that is as distinctive as the galaxy itself. These magnetic fields play a crucial role in various astrophysical processes, influencing everything from star formation to the behavior of cosmic rays. Just as galaxies come in different shapes and sizes, their magnetic fields also exhibit a wide range of strengths and structures. Some galaxies have well-organized magnetic fields, while others display a more chaotic arrangement. This diversity is a reflection of the complex and dynamic nature of galaxies themselves. Spiral galaxies, like our own Milky Way, typically possess a large-scale ordered magnetic field. This field is often aligned with the galaxy's spiral arms, creating a pattern that resembles a giant bar magnet. The alignment of the magnetic field with the spiral arms is not just a coincidence. It is closely linked to the processes that govern the formation and evolution of these galaxies. This field is aligned with the galaxy's spiral arms, creating a pattern that resembles a giant bar magnet. The magnetic field in spiral galaxies is not uniform. It varies in strength and structure across different regions of the galaxy. In particular, the field tends to be stronger in the spiral arms, where the density of gas and dust is higher, and star formation is more active. The magnetic field strength in spiral galaxies can vary, but it's generally stronger in the spiral arms, where star formation is more active. The presence of a strong magnetic field in these regions can influence the formation of new stars by affecting the motion of gas and dust. This, in turn, can impact the overall structure and evolution of the galaxy. Elliptical galaxies, on the other hand, present a different picture. These galaxies lack the well-defined spiral arms of their counterparts and have a more uniform ellipsoidal shape. The magnetic fields in elliptical galaxies are generally weaker and less organized compared to those in spiral galaxies. These galaxies lack the well-defined spiral arms of their counterparts. Instead, they have a more uniform ellipsoidal shape. The absence of spiral arms means that the magnetic field in elliptical galaxies does not have the same large-scale organization seen in spiral galaxies. Their magnetic fields tend to be weaker and more chaotic, lacking the large-scale organization seen in spirals. This chaotic nature of the magnetic field in elliptical galaxies may be a result of their different evolutionary histories and the processes that have shaped them over time. This difference may be related to the different evolutionary histories and star formation rates of elliptical galaxies. Unlike spiral galaxies, which have ongoing star formation, elliptical galaxies have little to no new star formation. This lack of new star formation activity could contribute to the weaker and more chaotic magnetic fields observed in these galaxies. Irregular galaxies, as their name suggests, lack a regular shape and structure. These galaxies do not fit neatly into the categories of spiral or elliptical galaxies, and often have a more chaotic appearance. The irregular nature of these galaxies is reflected in their magnetic fields, which are equally diverse and complex. Their magnetic fields are equally diverse, often exhibiting a complex and tangled morphology. The tangled nature of the magnetic field in irregular galaxies can be attributed to the various processes that have shaped these galaxies, including interactions with other galaxies and internal turbulent processes. The irregular nature of these galaxies suggests that their magnetic fields may have been shaped by mergers, interactions with other galaxies, or internal turbulent processes. These interactions can lead to the mixing of gas and dust, creating a more chaotic magnetic field. By studying the magnetic fields of different galaxy types, astronomers aim to understand how these fields are generated and how they influence the evolution of their host galaxies. This research is crucial for understanding the role of magnetic fields in the broader context of galaxy formation and evolution. This comparative approach provides valuable insights into the diverse processes that shape the cosmos. By comparing the magnetic fields of different galaxies, scientists can gain a deeper understanding of the underlying mechanisms that drive the evolution of galaxies and the universe as a whole.